What is force? Force is the push or pull on an object by the agent that created the force. For example, if you push a box that's on a table, then you are the agent because you are the one that is applying the force to the box. Now we're going to be talking about types of forces. One force is gravity. Gravity is the force the earth applies on an object. Gravity is what keeps you on the ground, and it is represented through F of G. Next is tension, which is a force applied through ropes or string. For example, these two ropes are applying tension force to the hanging block. The next type of force is friction, but we will be talking about it later on in the video. Then there's electric force. Also, air resistance is what happens when an object is falling and the air is pushing up on the object, slowing it down. An example is when you drop a piece of paper and it floats to the ground, and this is because of air resistance. Next is normal force. For example, when there's a box on a table, the gravity is pulling down on the object, like always, and there's also another force being applied to the object, which is the normal force. The normal force is keeping the object from going through the table. So in this example, the box is pushing down on the table and the table is pushing up on the box, which keeps it at rest. Finally is spring force, which is when an object is connected by a spring.
First, to make the force body diagram, draw the axes line, then place a point in the middle to represent the object we are examining. In this case, there is a person pushing a lawnmower at 30-degree angle. First, we are going to draw the force of gravity, which is pulling down on the lawnmower. Then we will draw the normal force, which is pushing up. Draw these two forces the same size because they have the same value. Next, we will draw the applied force, which is the force that the person is applying to the lawnmower. We will call this force F of A. For horizontal forces, this is the friction acting on the lawnmower. Don't forget to draw the angle, and it's measured to the diagram. Let's start with the equation for Hooke's law. The equation is F is equal to negative kx. X represents the displacement of how far you pull the spring down. The negative k represents how strong the spring is resisting the pull. If you multiply these together, you will be able to find the force being applied to the spring. Earlier, when we were talking about types of forces, we mentioned friction. Friction is the resistance against an object when there is a force being applied. For example, we have this box just sitting on the table, and there's no friction here since it is at rest. But if someone were to push on the box and make it move, then there would be friction acting on the box.
Newton's first law states that an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an unbalanced force. For example, this box is at rest and it will stay at rest because there is no unbalanced force acting on it, since the normal force and the force of gravity cancel each other out. If someone were to push this box, it would not be at rest anymore because an unbalanced force was applied. Inertia is the resistance an object has to a change in its state of motion. For example, when someone is sitting in a car and the car stops suddenly, the person is jerked forward. This is inertia because it is the person's resistance to the car's change in motion. Mass is the quantitative measure of inertia, and it is measured with grams. Weight is the gravitational force on an object, and it is measured with pounds. Equilibrium is when a vector sum of the forces acting on an object is zero. For example, if a box is sitting on a table, it is in a state of equilibrium because it is not moving, which means all the forces acting on it cancel and equal zero. On an FBD, the forces on the box are the normal force and the gravitational force. Since the box is not moving up or down, that means that the normal force and the gravitational force are equal. Since one is in the negative direction and one is in the positive direction, they cancel each other out to equal zero. There are no forces in the horizontal direction, so you don't have to worry about that. Newton's second law states that acceleration is directly proportional to the net force, and it is also inversely proportional to the mass.
Apparent weight is how heavy you feel. If you're on an elevator, it accelerates up. You feel heavier than usual because the elevator is starting to accelerate up. When in the middle of the ride, you feel the same as you always do because you are not accelerating. In this instance, it is the same as your normal weight. And when you are coming to a stop, you feel lighter because you are decelerating. To draw the FBD for block 2, in this case there are 3 forces. F of N because the table is pushing up on the block. F of G because gravity is pushing down. Since there is no vertical motion, these 2 forces cancel out. Then there is F of T. This is how the block 2 is being pulled by block 1. For block 1's FBD, there are 2 forces, F of G, which is the gravity pulling the whole system down, and F of T, which is pulling up.
And we're going to start with the general force equation, net force equals mass times acceleration. In this case, we are going to be solving for acceleration. We are going to figure out what we know and what we don't know. We can start by replacing net force with Fg1. The mass on the other side of the equation is referring to the mass of the whole system, so we're going to give it the subscript SYS so that we know that it is talking about the entire system. Then there's A, which is what we're trying to solve for, so we'll leave that alone. We don't know Fg1, but in the past we have learned that F of G is equal to mg, so we're going to replace Fg1 with mg. Then, since it is Fg1, we're going to take the mass of block 1, so we will give the m a subscript of 1. Next, m subscript SYS is the mass of the whole system, which is m1 plus m2. Then, times acceleration, which still doesn't change. Now that we know every value except the one we are solving for, we are going to rearrange it all so that we get a alone on one side of the equation. So there we get a equals m1g over m1 plus m2. Then we can replace all the variables with numbers. A equals 5 kilograms times 9.8 meters per second squared over 5 kilograms plus 12 kilograms. Once this is simplified, we have our final answer for acceleration, which is 2.9 meters per second squared. Again, we are going to start off by doing the general force equation. For this problem, we are solving for the tension force, which is only being acted upon by block 2. When you look at the FBD for block 2, F of N and F of G cancel out, which means that the net force for block 2 is just F of T. So F of T equals m times A. For m, just like on the last problem, we are going to give it a subscript. In this problem, the mass is just referring to the mass of block 2, so we will give it a subscript of 2. Then do not do anything to the A. So now we know m subscript 2 and acceleration, and what we're solving for is by itself on one side. We are done with the variables, so we can start replacing them with numbers. So the mass of block 2 is 12 kilograms times the acceleration that we found in the last problem, which was 2.9 meters per second squared. The tension force of block 2 is 35.9 newtons. Newton's third law states that when one object exerts a force on another object, the second object exerts on the first an equal force in the opposite direction. For example, if you're punching a wall, then you exert force onto the wall, and the wall also exerts the same amount of force onto your hand in the opposite direction.